In Web3, a single bug can mean permanent loss, not just an annoying outage. This course is about engineering trust into decentralized systems, from smart contract code to development processes and governance. We'll treat security not as a feature, but as a prerequisite for existence. To understand Web3 security, contrast it with Web2. In Web2, if something goes wrong, an admin can reverse a transaction, hide internal logs, and push a quick patch. Trust is placed in the company operating the servers. In Web3, there is no safety net. Transactions are immutable, the code is public, and trust shifts from institutions to cryptography. A single bug isn't a ticket to a hotfix. It can mean permanent, irrecoverable loss of assets, as several high-profile exploits have shown. In decentralized systems, security isn't a feature, it's survival. Before worrying about Solidity syntax or gas optimization, you need the right security architecture. Think of your dApp in terms of confidentiality, integrity, and availability. Confidentiality is controlling who can see what, typically through encryption and careful access control. Integrity is immutability. Once data or state is committed, it can't be tampered with. Availability is uptime and resilience under load or attack. To uphold all three, apply least privilege. Each role only gets the permissions it truly needs, and layer defenses from UI input validation down to data storage and key management. Unit tests are essential, but they only explore the visible surface of a contract's behavior. You choose some inputs, some edge cases, and see whether anything breaks. That does find bugs, yet it never proves that no bugs remain. The risk lies in the submerged part of the state space. Rare interleavings, unexpected call sequences, reentrancy patterns you never thought to test. In Web3, those hidden paths can lead directly to permanent loss. Formal verification tackles this by modeling all possible executions against precise specifications, aiming not to sample behaviors, but to mathematically prove that forbidden states are unreachable. Now let's zoom into how formal verification runs in practice with the VeriSol pipeline. It starts with your Solidity contract and its access control rules. These are automatically translated into an intermediate language called Boogie, which is much easier for verification tools to reason about. A solver then explores all relevant execution paths of that Boogie model using bounded model checking. From there, you get one of two outcomes. Either a mathematical proof that the contract satisfies the specified properties, or a concrete counterexample showing exactly how an invariant can be violated, so you can fix a real exploitable bug. Next, consider how semantic conformance can quietly break in a smart contract. Imagine an asset transfer that should move through three states. The buyer accepts, the seller accepts, then the transfer is finalized. A bug allows the code to jump directly from buyer accepted to finalized, silently skipping the seller's consent. The syntax is valid, but the business rule is violated. To prevent this, we instrument the contract with hoard triples, clear preconditions and postconditions around each function. These logical guards enforce the allowed state transitions and let formal verification prove that no invalid path is ever taken. To keep security systematic, we use the Smart Contract Security Verification Standard, or SCSVS. Treat it as a checklist of controls covering how you design, code, and review a dApp. It asks, is the architecture sound? Are access controls enforced? Is blockchain data handled safely? Are arithmetic operations and gas limits correct? Does the business logic actually match the intended rules? You can apply these controls 3 times: during threat modeling before you write code, during development for internal self-audits, and after implementation for external reviews. The result is a repeatable, auditable security baseline instead of ad hoc checking. To make Web3 security sustainable, you need a lifecycle, not just a checklist. It begins with design, where you threat model key flows and apply standards like SCSVS v1 before a single line of code ships. Then comes secure coding. use input validation and well-reviewed libraries instead of reinventing primitives. Next is verification, where automated tools and formal methods try to break your assumptions. After that, auditing combines simulated attacks with deep code review. Finally, maintenance. Monitor production, patch quickly, and track dependency risk. Mature teams don't run this loop once. They repeat it for every significant change. Governance in Web3 lives in a tension between code and people. On-chain governance is hard-coded, immutable, and automatically enforced. That sounds ideal, but it often becomes rigid and plutocratic, where money equals power. Off-chain governance sits at the other extreme, social, flexible, and driven by human discussion in forums and voting tools. It captures nuance, yet it's usually non-binding, so decisions can be ignored. The DAO hack in 2016 exposed this paradox. The community chose a hard fork, using social consensus to override supposedly immutable code. That moment proved that even in decentralized systems, human judgment can and will rewrite the rules. Flash loans turn token-based governance into an instant, high-stakes attack surface. An attacker borrows a massive amount of governance tokens for a single block with no collateral, as long as they repay within that transaction. While holding this temporary voting power, they push through a malicious proposal that would normally never pass. That proposal might transfer treasury funds to their own address or weaken key security checks. Once the proposal executes, the funds are drained, the flash loan is repaid, and the attacker walks away with the profit. The Beanstalk DAO incident, losing $182 million, followed exactly this pattern. Many decentralized protocols add a security council as an emergency brake. It sounds safe, but it quietly recentralizes power. A small group with the authority to override the system becomes a single point of failure. Because their identities are public, they can be coerced through legal threats, regulation, or plain blackmail. At the same time, many council members are closely tied to the core development team, creating conflicts of interest between what is best for users and what is best for insiders. The core lesson is that any privileged escape hatch must itself be treated as a critical security risk. Token-based governance assumes one token equals one vote. That sounds neutral, but it concentrates power in large holders, enables flash loan attacks, and turns governance into capital allocation. To engineer trust, we move toward meritocracy. One verified person, one vote. That demands reliable identity without recreating Web 2 surveillance. Proof of Humanity offers decentralized, video-based verification, while soulbound tokens bind non-transferable reputation or membership to a wallet. Together, they provide Sybil resistance, limit vote buying, and reward long-term contributors instead of short-term whales. The result is a governance layer that aligns economic security with real community participation. To fix governance, we must protect voters from coercion, not just secure the blockchain. Zero-knowledge proofs let someone prove they're eligible to vote without revealing who they are or how they voted. Fully homomorphic encryption goes further. Votes are encrypted before leaving the voter's device, yet the system can still compute the final tally directly on those ciphertexts. Only the aggregate result is ever decrypted. The key outcome is coercion resistance. If no one can prove how they voted, then bribery, vote buying, and many physical threats lose their leverage, dramatically increasing the integrity of decentralized governance. Algorand's governance model blends the strengths of off-chain discussion with on-chain guarantees. Proposals start in familiar spaces like forums and GitHub, where ideas are debated, refined, and clarified without spending gas or clogging the chain. An expert XGov layer then filters and shapes these proposals, translating community needs into technically sound, fundable grants. Finally, the broader set of governors, who have soft-locked their tokens for a fixed period, vote on which proposals should be executed. If they move their stake, they lose rewards. That lock-in creates skin in the game, aligning incentives with long-term protocol health. Decentralization doesn't magically create trust. It removes the human middleman and forces the architecture to carry that trust instead. Think of your dApp as a fortress. The code is the foundation, formally verified, semantically correct, least privileged by design. The process layer is the defensive wall, SCSVS controls, repeatable reviews, and a rigorous security lifecycle that never really ends. Above that sits governance, identity-aware, Sybil-resistant participation and privacy-preserving, coercion-resistant voting. When all three layers reinforce each other, failures become contained, attacks become expensive, and users can rely on the system itself, not a benevolent operator, for safety.